Hey everyone. While we're waiting for more people to join, I know we're a minute after. I'll just go over some housekeeping here. Thank you everyone for joining our GET webinar today. Everyone is being recorded right now. The entire webinar is being recorded, and the slides and this recording will be distributed by the end of the week. If you have any questions, feel free to raise your hand or put in the chat if you want to go off of mute, or throw your question in the chat. We'll get to it at the end. And with that, I'll pass it on to our presenters and they can share their screen.
Perfect. Thanks, Kate. And then just confirming that everybody can see my screen okay.
Looks good.
Perfect. So thank you all for jumping on this dissemination for the energy efficiency modeling of GHPs project that's been done through the Gas Emerging Technologies Program, the SoCal Gas Emerging Technologies Program. My name is Madeline Talebi. I'm with ICF. I'm an energy engineer. I'll go ahead and let Jeff introduce himself as well.
Yep, thanks everyone. So I'm Jeff McGuire. I'm a researcher here at NREL, the National Renewable Energy Lab. And so I've been working with my colleague who couldn't make it, Joe Robertson, and Madeline on this project. Nice to see you all.
Thanks. So I'll go ahead and kick us off. So before I move on or continue through the presentation, just want to acknowledge all the project collaborators, so those from ICF, and as Jeff mentioned, some of the folks from NREL. So just a brief agenda, I'll touch on a little bit about the background and objectives. We'll go into the modeling scenarios, some assumptions, results, and then touch on some recommendations. So ultimately, this project covers gas absorption heat pumps. So previously, we have done projects through the Gas Emerging Technologies Program that have looked at the laboratory side of things. So that's been done with GTI Energy, and that's been looking at natural gas, a fully comprehensive test matrix. So essentially, with this project, we've pulled that data, those performance curves that were developed from the laboratory study, and that study is available on the GET website if you're interested in reading a little bit more about it. But this side now focuses on the modeling side using Energy Plus. So in terms of the emerging technology, as I mentioned, is the gas absorption heat pump. On the previous slide, it is the Rober GHP-A model. And so why we're interested in GAHPs is ultimately they kind of unique to this technology. They use heat from natural gas combustion as opposed to electricity to transfer heat from outdoor air to indoor air. And so why we're looking specifically at water heating, it is the largest non-industrial end use of natural gas in California. Therefore, there's a wide breadth or market available to kind of look at in terms of energy efficiency savings. And so the focus sector in this case is going to be multifamily. And I've included some California bills, legislation, standards, plans that kind of echo this sentiment of wanting to look at honing in on the focus sector of multifamily. There's a lot of opportunity based on where current California bills and legislation are kind of leading us towards. And so for that reason, we're focusing on multifamily in this case. And so the modeling workflow I've included down here. Jeff will probably go into this, or most definitely go into this in more detail, but just to give a high level. So we have we essentially start with the RESTARC housing characteristics. Then we move to the sampled build stock CSV file. Once we define everything, then we can kind of compile everything, develop an HPXML file, and then transfer that over to OpenStudio or the Energy Plus module. So OpenStudio and Energy Plus were kind of used in parallel with one another, and then ultimately take that into our output or the simulation results. And so some objectives before I pass it over to Jeff. So essentially we want to take, as I mentioned previously, develop performance mapping curves that were gathered from the GTI Energy laboratory study of the GHP-A model and integrate that into RESTARC and Energy Plus modeling software. And I have the laboratory study referenced here as well if you're interested in reading more on that report. And we want to leverage RESSTOC to ultimately forecast annual energy use, operational costs, so that being utility bills, and then greenhouse gas emissions. And the target sector is going to be California multifamily housing across the 16 climate zones, which currently utilizing a large central boiler to satisfy load. That's kind of what we found is the one-to-one comparison between the two and looking to essentially retrofit with a GHPA model. And so with that, I'll go ahead and pass it over to Jeff.
Great, thanks, Madeline. A lot of people here might have some familiarity with RESSTOC, but I'm going to go through it in a little bit more detail here. So RESSTOC is an NREL developed tool that we have for modeling the entire residential sector of buildings in the US. And so the way we do this is that we have this kind of characterization of the stock. So we'll have probability distributions that represent the housing stock as it exists today. So we'll have distributions for different characteristics like the size of buildings, insulation levels, things like that for different locations all across the entire United States. We now cover all 50 states. And so when we have those probability distributions, we'll then do sampling. Sampling and the model articulation are actually backwards here, but the text at the bottom is correct. So we will sample out of that housing stock to get sort of representative samples and enough samples that we think that we can accurately represent the entire stock across the entire US, or if we want to down select specific regions, enough samples to represent that region. So for example, in this case, we are trying to represent the multifamily stock in California. And so we don't need as many samples as we would for the entire US single family, multifamily. We're just focused on that one sector. Once we have the samples and the representative number of samples selected, we can then do the model articulation. So translate those samples and those higher level characteristics that were in the probability distributions into the more detailed information that a building energy model will need, and create building energy models for each sample that we have. We can then do some batch simulation. So running all those building energy models, we have the advantage here of having a supercomputer that we can use for doing this. You can also do this with AWS if you want to do your own runs. And then finally, once we have results, we'll do some publication and analysis on those results. In this case, we're publishing a final technical report here. For some of our like national scale runs and the standard data releases, we also publish a lot of the data becomes available as well. We can go on to the next slide here. And so for this study, we are down selecting to this, and we have a couple different scenarios that we're considering here. So our first scenario is our 2020, which is kind of a baseline year. I do realize what year it is, and I know that's several years in the past to use as a baseline, but it takes time to get statistically representative data. And so most of the data that we have is pretty representative of around 2020-ish. So that's our standard baseline year for a lot of our releases. Then with that, we are doing projections into the future. And so going scenario 2 is looking at 2023, where we're doing some projections. We're trying to account for code for any new buildings that get built. We also account for any demolitions that might happen, and we're using a projection tool to do that. And then we have different scenarios with different electric and gas efficiency here, and different electrification percentages. Scenario 3 is going another 3 years into the future, looking at 2026. And so we look at what would happen with code, using what code looks like for 2026. For electric efficiency, you might see electric heat pumps, and then on the gas side, you might see condensing water heaters. We have some electrification by end use. We're trying to account for local policy, although local policy is constantly changing. There's details in the report on when exactly we pulled data on that local policy that we're using here. For 26 and 29, we have A and B scenarios. And so the B scenario is looking at kind of more aggressive gas efficiency measures. And so you can see in our 3B is when we have some percentage of homes getting gas absorption heat pumps, along with additional gas efficiency measures. And then as we go into 2029, we have code being applied again, and then we also have more aggressive gas efficiency, and you can see a higher percentage of gas absorption heat pumps, up to 6.5% of the stock. For existing buildings, we do also have, you can see in the bottom left here, we're trying to account for some turnover of the things that are especially relevant. So central water heaters, about 20% of the stock turns over every 3 years. And then PV is another thing that we saw appreciable turnover for. So 1% of the stock gets PV every 3 years. And other things are assumed to basically not be either not be upgraded or their upgrade isn't particularly relevant to the analysis that we're doing here. Next slide. So this is kind of showing some of the results of the projection tools. This is just sort of showing the count of the housing stock across different climate zones that we have here. So you can see in general, it increases over time, as you would expect. There's some demolitions, but certainly more stuff is being built than things being demolished. The other thing that you can see here is how this kind of breaks down by climate zone. So we're going to show results across all 16 climate zones, but we do account for where buildings are and how that impact climate zones. So you can see the more populous climate zones tend to have more buildings. And you can see also the number of buildings in those climate zones kind of increases more than it does in some of the less populated climate zones. Next slide. This is also looking at some of the unique characteristics. So along with the stock, all the characteristics of that stock is changing over time as well. So you can see here, we're kind of just focused in on water heater fuel, but other characteristics are also changing. And so you can see here that the fuel being used does change over time. The stock, there's kind of more electric water heaters being added to the stock, but you can see in our gas efficiency scenarios that having the gas efficiency measures does change that a little bit. And so you see more natural gas use in the gas efficiency scenarios. So that's the 26 gas efficiency and 29 gas efficiency. Sometimes we have these labeled as A and B. Next slide. Okay, I'm going to go through kind of some of the modeling that we did here. This is using ResStock, but ResStock didn't have at the start of this project the ability to explicitly model large multifamily buildings with central domestic hot water loops. So we actually added a lot of this functionality in as part of the project. This is just a high level overview of what these sort of systems look like. So on the left here is kind of what you might see typically in an existing building. So you have a boiler that's paired with a storage tank. In reality, you might have multiple. We're kind of combining all those and doing sizing calculations to account for like the total system size that you might have. Then you have that storage tank going into the central domestic hot water loop. And then that returns and comes back in, and eventually the boiler will reheat that. On the right here is our retrofit, where we're adding in a gas absorption heat pump. So you can see that here where you have the gas absorption heat pump paired with its own separate storage tank. And that's the first tank in the system. And then we're retaining the existing boiler as a backup. So the heat pump will see the coldest temperatures coming out on the return. It'll try to heat the load. If for whatever reason the heat pump can't heat the full load, then the boiler will kick on to make sure that you are maintaining adequate hot water for those dwellings. And then I think if we move on here, we can start looking into, on the Energy Plus side, what some of these specific loops look like. Yeah. So first, we're going to go through the scenario on the left here and look through some of these specific loops and what this looks like in Energy Plus. Yeah, it's fine. You can move on to the next slide. So this is, I'm going to go through all the different, they're called plant loops in Energy Plus terminology, but go through all the different loops that we combine here for what the Energy Plus model looks like that kind of represents that scenario that was on the previous slide. The first loop we have here is the supply loop for the boiler. So we have the boiler with a set point manager on it that tells the boiler what the set point should be and what temperature it's trying to provide into the storage tank. And then when there's demand, the pump will turn on and the boiler will run and it'll provide hot water into that storage tank on the bottom there. If we then go on to the next slide, I think we will see the storage tank supplying hot water. And so this has a pump associated with it and actually supplies hot water. We have this kind of fictitious heat exchanger here. This is a perfect heat exchanger. It's 100% efficient. There's no real losses associated with it. It just kind of makes the modeling easier in that we can split these out into a couple different separate loops here. So we have different things on the supply and return side. And then I believe if we go to the next slide, we'll see, yeah, this heat exchanger is on the supply side here. And then that has a set point manager associated with it. The set point is the temperature that's actually going to the domestic hot water use in the building. And then we have supply and return pipes here along with the water use equipment. So we have explicit models for all the pipes that are in this building. So we have real recirculation losses associated with those pipes. We are doing some calculations based on the building geometry to determine what we think is an appropriate length of piping. And then there's assumed levels of insulation on the supply and return here. We have hot water use equipment. So this is the domestic hot water use in each unit. We have a tool that is incorporated into ResDoc that lets us calculate stochastic domestic hot water usage. So we're assuming for each occupant that there's some sort of occupancy schedule that they're following and that they're drawing different amounts of hot water at different times. And then all that hot water usage gets kind of summed up into the net domestic hot water draw profile. We also have a recirculation pump here. So we're assuming there's basically constant recirculation so that there's always hot water available to all of these units, even if they happen to be pretty far away from where that boiler might be in the building. I think we can move on to the next slide here. So that's kind of our existing system architecture. And then we also have on the right here this retrofit scenario. And so we can start going into that and what some of these different loops might look like here. So here we have the gas absorption heat pump loop. So we have this on the supply side of the loop. So it's applying hot water to the storage tank that's paired with it. Has a set point manager on it as well, and there's a pump associated with that for the flow here. We can potentially have multiple of these, and I think one of the other loops will show multiple of these. We do some sizing calculations. I believe the assumption is that for every 20 units, we add another gas absorption heat pump. So we can have multiple of these kind of paired in series to try to meet larger loads. If we move on to the next slide here, we can talk a little bit about what this gas absorption heat pump model looks like in Energy Plus. So this was a relatively new object added to Energy Plus. I think we were some of the first users of this object since it's been created. So we got to test it out. We also, being some of the first users on this, noticed and got fixed an issue with this object in Energy Plus that had to do with how the curves were being used. This should all be fixed, so any release of Energy Plus, any recent release will have that fix associated with it, so not something people will have to worry about in the future. But this model uses basically performance maps, so it takes the data Madeline referenced and provided the reference to the report for the lab testing GTI had done here to characterize the performance of this unit. And so we're using that data kind of to generate these performance maps like you can see in the upper right here, where we might have performance of the gas absorption heat pump. So different capacity and COP values, depending on the ambient air temperature, so the outdoor air temperature in this case, because these are installed outside, and what the water temperature is going into the heat pump. So this lets us characterize the performance of these units, and this lets us also take into account the impacts that different climate zones might have because they'll see different outdoor temperatures. Another thing that we did as part of this project is that it was seen in the lab testing that it takes roughly 20 minutes or so to hit steady state conditions for this unit. And so the COP of the unit during startup can be less than the nominal COP. So we wanted to account for this in Energy Plus. Energy Plus, a lot of the time, doesn't have a lot of really explicit models of cycling. But it does have this custom scripting language called EMS that lets us add in custom code to do whatever we might want to do if we have something like this that's not core to Energy Plus. So what we did as part of this project is you can see here that using 15-minute time steps, this custom EMS script basically calculates what the CLP should be based on how long the heat pump is run. So if it's starting off in the first 15 minutes, we try to account for the fact that the CLP doesn't reach the nominal capacity. By the time you hit the next time step, 30 minutes out, it's more or less hit its nominal capacity. And then from then on, it runs at basically the steady state capacity. So this lets us use some of the custom scripting to account for these more complicated scenarios and make sure that we're accurately portraying the efficiency of these units here. All right, I think we can move on to the next slide. This loop is actually basically the same as what we saw previously. This is, again, retaining the existing boiler as backup. So we have the same storage tank and the same boiler retained here. We do sizing calculations for these based on basically the ASHRAE method. I think there's a lot of active projects around different sizing calculations. So this could potentially be adjusted in the future. And then if we move on to the next slide, we'll see here, this is how we have the gas heat pumps, in this case, 3 of them, configured combined with the boiler storage. So we actually, in this case, have 3 storage tanks. Each gas heat pump is paired with a separate storage tank. These are all in series configuration, then feeding into the storage tank associated with the boiler. So the first heat pump will run most of the time, then the second one if there's still need for load, and so on and so forth. One thing that we were interested in but not able to do in this project was parallel configurations of these storage tanks. There's probably more efficient ways to do this than having everything be in series here. There are some limitations in Energy Plus, not so much around setting up the plumbing, but around how you actually split out the load in parallel configurations. So that might be something to explore in the future. We do think that with the series configuration, you're maybe not getting the max efficiency you could get out of these, because by the time you get to the third heat pump, you have water that's already been heated quite a bit. And so the efficiency of that third unit might be a little bit less. Whereas if you kind of split it out so that you had colder water going into all 3, you could potentially maybe get a little bit more efficiency out of these units. So I just want to mention that as a potential limitation here. I think we have this kind of highlighted as potential future work as well, just on the modeling side. And then, yeah, this side of the loop again looks basically the same, regardless of whether you have the gas heat pumps here or not. We're keeping all of the distribution, and the hot water use is basically the same. We just have different things on the supply side, so you might get more efficiency in terms of how this hot water is provided to the occupants. Okay. Yeah, we can go through some results here. The report will have a lot more results in a lot more detail, but we're trying to kind of highlight some of the, excuse me, some of the higher level results here, looking at all these different scenarios that we have. So we're going to be going through statewide energy use, utility bills, and emissions. So this is looking at hot water and natural gas use across all these different scenarios. So scenario 1 here is our 2020 baseline year. And then 2023, you have some applications of code to new construction as that gets built, as well as some amount of the housing stock being retrofit. And so then you get some efficiency associated with that. As you move into 2026, we have the A and the B scenario here, where A is assuming some electrification along with the 2026 and Title 24 and the efficiency measures that were shown in the earlier slide for our scenarios. The B scenario has the gas absorption heat pumps associated with it and some additional efficiency on there. So you can see what the impact of those efficiency assumptions would be. With the efficiency assumptions that we have here, that's actually reducing the per unit average, which, keep in mind, some of the housing stock is not getting these efficient upgrades applied to them. more than just natural stock turnover by the year 2029. And then in 2029, when we start looking at the B scenario, we have more aggressive adoption of gas efficiency, which is largely what's leading to that the higher per unit savings in that scenario here. So this is, again, the stock level average, which means that not every building is getting this applied. In several slides, we'll kind of dig into like the specific impact of the gas absorption heat pump for the dwellings that are getting those. I think we can, move on to the next slide here and look at the utility bills. So we do utility bill calculations here. We're accounting for gas and electric bills. For this presentation, we're just kind of focusing in on the natural gas bills. On the electric side, we're doing calculations. We assume some rate of fuel escalation for future years based on what's been seen in California recently. We're assuming that the gas, there isn't really substantial escalation in those costs. You can see here that the gas bills are somewhat proportional to what was seen in terms of the savings on the per unit basis. We do have fixed charges here, as well as the variable charges with fuel use. So you can see, because the fixed charges are kind of the same regardless of the efficiency, that kind of mutes the savings from the utility bills, but you can still see that there's some pretty substantial savings that can be seen across the stock here, depending on the different scenario that we're looking at. If we then look at the next slide, I think we have the emissions here, looking at the net emissions for hot water and trying to do the per unit average here. For gas, we have a pretty flat emissions factor of a certain amount of CO2 equivalent per therm used, basically. On the electric side, we're using a tool that NREL developed called Cambium that accounts for the mix of generation and the time varying of that mix of generation to try to account for like what the emissions factor is during different times of day when there might be high penetrations of renewables versus low penetrations of renewables. This is looking at the per unit average hot water. A lot of this is natural gas, but there's some electricity use associated with this. Even for the dwellings that do have, that are using natural gas, there's still some electricity consumption associated with pumps and standby controls and things like that. So there is a little bit of electric use even for most of the homes that are using purely natural gas. And you can see here by far the biggest savings is that 4B scenario, which has the most aggressive natural gas measures being applied to it. I think if we move on here, we're going to start trying to dig into specifically the impact of the gas absorption heat pump here. So the next two slides, we are filtering down the results to look at 2029, our future year scenario with and without gas heat pumps. So we have the 2029 A and B, and this is just filtered to the homes that in the B scenario are getting a gas absorption heat pump. In the A scenario, they do not have that. So what we're really seeing here is the savings that's provided by switching from what they had in the existing to using a gas absorption heat pump. So it's the savings from having basically a non-condensing boiler to having the gas absorption heat pumps, as we showed the plant loop layout, and then those being used with that boiler being retained and potentially being used for backup occasionally. You can see here is still reflected in this is the number of dwellings that are in each climate. This is net use, so number of dwellings is still a factor here, but you can see that the percentage savings does also change with climate zone. So for example, in climate zone 8 and 9, you can see higher percentage savings than you see in climate zone 3. This is due to a variety of factors. So the ambient air temperatures are different. The incoming cold water temperature is different. The performance map is sensitive to both of those. There's also differences in the housing stock in terms of the number of dwelling units that are seen in some of these, and one interesting thing that we did see was that the savings potential is kind of lower for the more dwellings you have. Part of that is probably due to the series configuration. But basically, all of those factors are in play here when we start looking at the efficiency savings. 8 and 9 were kind of the most savings that we could see across a climate zone average. If we then, look in here at, we're doing some XY scatter plots here to try to look in a little more detail at some of the characteristics that matter. So this is showing on the y-axis here, or sorry, on the x-axis here, we have kind of the baseline fuel use for each sample, basically each multifamily building. And then on the y-axis here, we have the energy use in the upgrade case. So when gas efficiency is applied, you get a gas absorption heat pump. And then we have the line at the top there is basically no savings. And then we have kind of 20%, 40%, 60% savings. This is just looking at energy use. And we're trying to kind of split out the number of dwellings here. So certainly there's a lot of scatter and spread in this because this isn't the only factor that matters. But you can see as a general trend that as you start getting to some of the bigger buildings, especially the ones that you start getting large numbers of gas absorption heat pumps, you see less and less savings. I think we do eventually cap the number of gas absorption heat pumps that get installed as well. So I don't know that we'd ever install 15 for, say, a 300 unit building. I believe the max is 10 or 12. But even with that max, you can sort of generally see this trend that for larger buildings, you get kind of less savings. So there's maybe kind of a sweet spot to target based on the number of dwelling units as well. I think if we move on, let's see, Madeline, I think you wanted to run through the takeaways. Is that right?
Sure, I can touch on these and feel free to add any gaps if I miss any. So in this case, thanks, Jeff, for kind of going over all the different scenarios that you guys did and the results. So ultimately, just to summarize everything, so some of the key takeaways from this project. So as Jeff mentioned, they made significant updates to RESTOC for whole building shared water heating system simulations. So that was kind of a positive development in all of this. So that was fun, good to see. And then ultimately there was a bug fix in Energy Plus, as Jeff mentioned. Any future release of Energy Plus will have that correction included. And then this was a big portion too in terms of taking the laboratory data, which does show about a 20-minute steady state period, or to reach the steady state period. And that was pulled from the GTI Energy lab testing. And interestingly enough, we saw that there is a similar, somewhat warm-up period, or I guess, I guess you can call it a warm-up period for the lab study and the field test. So that was good to see that there was a similar comparison, and ultimately that included in the RESTOC GHP model. And then ultimately looking at the energy consumption, utility bills, and emissions, they did decrease across the 4 scenarios and sub-scenarios for the 16 California climate zones. So maybe I'll pause here for the key takeaways in case, Jeff, there's anything else that you kind of wanted to add in this section.
No, I think this is great. I would just, there's certainly a lot more detail to dig into in the report. And so that should be published shortly, and you should be able to see all the detail if you want to dig into it.
Yes, yeah, we will have that up. So that report is not currently on the website, but we will have that up in about a couple weeks. And so if any of you are hoping to not have to check, you can reach out to me or Ava, and I can shoot you an email when that is available on our website. And so future studies, as Jeff mentioned, this is done in series, so it would be interesting to see kind of a series versus parallel tank configuration exploration where that's feasible. And then look at RESTOC updates to reflect the year-over-year changes to local electrification policies. And then ultimately, this is somewhat in the works, but looking at to potentially a comprehensive GHP design tool, which factors in several OEM GHP performance mapping data. So through the GET program, we've done several studies, that being lab, field, different OEMs. So this would kind of somewhat be a comprehensive study, which would be interesting to look at. And so with that, yeah, if you would like to get in touch with myself or the program manager for the GET program, Ava Donald, please feel free to do so. And I think at this point, we'll take any questions.
I think we got some questions. We have one in the chat, and then we have one in the Q&A. We have two in the Q&A. Madeline, can you see either?
Yes. Yeah, I can see both the Q&A and the chat. Maybe we'll start with the Q&A. Jeff, can you also see the Q&A questions?
I can see the chat, but I cannot see the Q&A questions. It says Q&A is not available for this event.
Oh.
So
okay, I'll drop those. I'll copy and paste them into the chat.
Okay. While you're doing that, I might start with the first one in chat. Apologies to the folks in the Q&A, and we'll get to your questions shortly. I think we have more than enough time to handle everyone's questions here. So in terms of the Energy Plus objects that are being used here, for modeling the water heater, we're using the stratified tank models. So we do have it configured so that the boiler or the gas absorption heat pump is basically pulling from the bottom of the tank and delivering hot water into the top of the tank. We think we have enough nodes here to be accurately representing the stratification, and we think that's actually kind of an important thing to account for here, especially when we're trying to use a temperature differential for control on this. So yeah, stratified tank models. For the tankless system, there isn't an explicit tankless model in Energy Plus. I know this has been proposed a couple times to have something that actually has the mass of the heat exchanger associated with it. We're kind of using a simplified approach where we're basically assuming that the efficiency is relatively constant of the tankless. We do have some D-rate that gets applied to account for cycling of the tankless system. I believe the efficiency is 6% less than the UEF of the system, if I recall right. That D-rate comes from ANSI ResNet 301 standard in terms of what they say an average D-rate ought to be. So we're just trying to be reflective of that. Regarding the ambient air source, so for the gas absorption heat pumps, they're all assumed to be installed outside, so they're seeing outdoor air, not any sort of zone air temperature. I think that goes through all those, but if you have any more questions, feel free to put them in the chat or come off mute and ask. Next one I see is from Melissa. So for larger buildings, we get less savings, so we might target a certain number of units. Yeah, good question about the sweet spot. I think there's some practical considerations here too that we maybe can't account for. So yeah, while we see sweet spots around, I don't know, maybe 60 to 100 units, roughly speaking. And there's a lot of other factors that confound that. So I don't want to say like that's definitely just do it purely based on number of units. I think you also have to consider like how feasible it is to actually fit all those storage tanks in the building and fit all those gas heat pumps outside. So yeah, we do think that there's probably certain buildings that you might want to target, but there's lots of other factors beyond just the number of units to consider. But just as a rough answer, something in that 60 to 100 range is probably reasonable to target. Let's see, from Ram here, boundary conditions from daily hot water demand versus sizing the equipment. So was there a cutoff for multifamily buildings with peak hot water demand of X gallons per day set as the minimum for this analysis? We are somewhat simplifying things here, where we are saying that there is, we're doing it just based on the number of units. We could try to do things based on more the number of occupants, or since number of occupants can change, especially multifamily where people move in and out all the time. We could do it based on number of bedrooms or something like that. I would say what we're doing here from a sizing perspective for the gas absorption heat pumps is definitely a little simplified. There's probably more nuanced ways to do this. And there could be a whole sizing study that gets into that. So we think what we have here is kind of roughly all right. And we did try a few different things to make sure that this looked like it was somewhat okay. But you could kind of get a little more details with it if you wanted to. And let's see, where there scenarios evaluated where the recirculation load and return is fed into the main storage tank, rather than feeding into the gas absorption buffer swing tank. We did not consider that scenario as part of this study. I think you could look into different plumbing configurations. One thing that I forgot to mention is that the workflow here is all public. There is I believe it's a public GitHub repository. I believe it's called Get ResDoc, and I could put a link into the chat, so anyone here has access to it. But there is a public repository where people can go and use this. There's a little bit of documentation associated with it too. People could go in there and if they want to try to set up alternate configurations. Right now we're kind of publishing things as is at the end of the project, and we're not doing a lot of maintenance work or upkeep on that. You might see that there's some branches of that repository that are getting used for other projects by folks here at NREL. But a lot of the gas absorption heat pump stuff is pretty static. Certainly, we could look at modifying this in a future project, or you could look at modifying it yourself if you're an Energy Plus modeler and so inclined. Let's see, Christelle, about the savings for more multifamily units. I think part of that is the series configuration, and we kind of have hotter water being fed in, and then the third heat pump kind of might see less load and be running in less favorable conditions. We do think the parallel configuration that might actually be a little bit better, especially when you start getting to very large numbers of heat pumps. You have a lot of the time where there isn't enough demand if you have everything in series where the 10th heat pump really needs to run all that often. So you also see that 10th heat pump might be short cycling quite a bit. And that might be dropping off its efficiency as part of this series configuration. So I do think part of this is just kind of an artifact of the way that we're doing this modeling. And there's probably ways to design around this that are just sort of outside the scope of what's feasible in the Energy Plus models and with the budget we have for this study. Does that kind of make sense, Christelle? I see.
Yes. Sorry,
okay.
Did you say 10th heat pump, Jeff?
Oh, I mean, in some of the really big buildings, yeah.
Oh, okay.
I'm going to an extreme case to kind of explain why, as you start getting to really big numbers, like it kind of going to the limit might be helpful in explaining where things start dropping off.
Okay, yeah, that makes sense. I actually had raised my hand though, because I had a follow-up question maybe for Madeline. Regarding the domestic hot water loads, I know that you guys are working on a design tool, and just anecdotally, the ASHRAE sizing is kind of high for what's reality, and it's really important that GAHPs have a minimum amount of load, as you know, I've been talking about in my field studies. So how are you planning to deal with that? Or yeah, just wondering.
Yeah, I think I'm not sure if I can comment too much on this at the moment, just because it is kind of in its developmental stages. But I think once we get the project kicked off, I think then maybe and I don't know if Stephen, I don't want to enter into territory I shouldn't be discussing at this moment. But yeah, since we haven't gotten to, I'll unmute Stephen on this case. You're unmuted, or you can, yeah.
Okay, can you hear me now?
Mm-hmm.
Yeah.
Okay. Yeah, I think that will be understood as part of the project, and even will probably be evaluated per that project. But as Madeline said, we're still working on scoping it out, so it's not an active project yet.
Jeff, do you have recollection, and I may just have to download the report, but if you had 100 units, do you remember how many GAHPs it said you needed?
I believe that we did one for every 20 units. So I believe the answer would be that we'd put 5 in.
Okay.
You probably aren't running all 5 all the time, right? So coincidence of load really matters in that scenario. But I think that was our rough sizing assumption here.
Okay. So maybe we should sync up later, but I have a field study with 70 units and I have 1 GAHP and it doesn't run for a full hour. So it's interesting that the ASHRAE sizing says you need that much, but that's not what I see at the field. So just wanted to point that out as a maybe research topic for everybody later on.
Yeah, no, that's great. And certainly I think, we could have done a sizing study like that. That would be a whole other simulation study, and it might be interesting to look into that, right?
Yeah.
We could have done every 30, every 40 units, however you want to do it. Certainly because this is published, there's a number in that code there that just says like how many units before you increment up the number of gas absorption heat pumps.
Yeah.
And so someone could easily go in and change that and do that analysis if they wanted to, even if just using what's public.
Ooh, okay, cool.
I'll add a little context because I think we had a discussion about that early on, and the indication was that 5 that you all modeled with was sort of the recommendation. But I'll point out something else that was discussed on some of the sizing analysis, Crystal, that was looked at, was that the loads are very variable. So it's not just the sizing, it's what's used as the load profile. And I'm not sure in the Restock, I'm not sure what the driver on the load profile. We know, what's, and maybe that's Jeff, maybe you've got a answer to that, because that's got a big impact as well.
Yeah, so we do have this stochastic tool for trying to generate the load profiles, but we also don't necessarily, once we start getting to big enough buildings, we do kind of repeat those. So you do end up with some of the loads kind of stacking up in a way that might not be entirely realistic. I believe it's once you get beyond 10 units, we start using this concept in Energy Plus called unit multipliers, which a consequence of using that is that if you have, say, a unit multiplier of 2, it's basically the same as saying 2 units have identical hot water draw profiles. Computationally, this is like really efficient, but we know it's kind of a limitation, right? And so
yeah,
in the past, we've seen in other studies, I don't even know that this was published because I think I did it like 12 years ago. We looked at 15 unique draw profiles versus 10 and then having them repeat, and we didn't see a huge variability in like the efficiency of heat pumps and how the load stacked up. And so we kind of thought this was an okay amount to repeat things. But like I said, this was like 12 years ago, and it's been a while since we did that kind of study. So maybe something to look into again, just kind of an assumption / limitation to be aware of in the results as we have them today.
Cool. Well, thank you so much. This was really great study. I'm very excited that this is done.
Yeah, sure. Happy to do it. We're happy to have all of these results out there and have the code out there for people who might want to do any other studies. I think we've covered all the questions. Is there anyone
I
who
think
has a
there's one
question?
more from Ram actually after you posted the GitHub link.
Oh, yes. Thank you. In the next release of Restock, I think all I can really say is we're currently in negotiations with DOE about what will be in the next release of Restock. There was a release at the end of last month. This was not part of that release. Right now, I think the plan is to do another release in the spring timeframe. I don't think this is planned to be part of that release, but those discussions are ongoing, so I can't really say with any certainty. what will be in the next release. I think there's a potential for this to be incorporated in the future. I just don't know when exactly. If anyone else has any questions, feel free to put them in the chat or unmute. It looks like we still have a few minutes here. Maybe not. And that's fine too. In that case, do you guys on the ICF side want to wrap stuff up? I'm gonna, I'll put my email in the chat too. If anyone thinks of something that's more a question about the modeling workflow, feel free to just reach out to me directly.
Yeah, just thank the presentation team, Jeff, Madeline. Appreciate the work and the insights, and thank you all for attending.
Thank you all.
Yep. Thanks, everyone. Take care.